Planning has begun for EWRI's 19th annual workshop coming up November 1st. The theme this year will be staying ahead of the curve. Additional info will come from that. And they're also currently accepting applications for the 2024 EWRI scholarships. Please submit those by June 2nd. More information can be found on our website under EWRI scholarships. Why that?
Hi everyone, I'm Newton here to give the YMF update this month. So upcoming events, we have the Shoal Creek cleanup June 1st, starting a little bit earlier to hopefully beat the heat. But 9:30 at Peace Park, if you're interested, we do have a sign-up link. It should be in the newsletter, but also on our calendar. We also are looking for our 2024-2025 YMF board. We have positions open, chair positions, committee positions. So if you're interested, you can email right there, YMF@awesomeasc.org, but you can also come find me. I can give you my card, we can chat. Just let me know. And then a huge thank you to everyone who came to our joint happy hour. It was last week with Kawa YP and the YP. And next, I have a few slides. We're going to announce our scholarship winners, recipients. Every year, we're able to award some scholarships. And yes, I'm gonna go ahead and do that. So I'll be basically reading these bios so you can read from the slide or listen to me. Our first recipient is Noah Chia. He is a graduating senior at ECU High School in Georgetown. This fall, he will be attending the University of Texas at Austin, where he is majoring in biology on a pre-medical track. He is extremely grateful for the scholarship and this step toward his goal of providing life-changing healthcare. So we can do applause at the end. I'll go to the next one. The next scholarship recipient is Jack Benveniste. He says he is hailing from Austin, Texas, currently a student at Westwood High School. He is serving as the captain of their water polo team. He is excited to embark on his journey into civil engineering at Virginia Tech University. And his long-term goal is to start his own company that improves public transportation infrastructure in cities like his own. And then our next recipient. Maybe we're missing a slide. Hold on, I'm going to jump ahead. There we go. Third recipient for the YMF scholarship is Christopher Chung. He is from Los Angeles, California, and is attending Cedar Park High School and plans on studying at the University of Texas at Austin to pursue his aerospace engineering degree. So huge congratulations to all of them. They're all highly qualified. Each year we get 30 to 40 applicants, and we have to go through a ranking process to determine these recipients. So they are definitely highly deserving. So huge congratulations to them.
Howdy everyone, my name is Fred Noble and I am on the ASCE Office Branch Scholarship Committee. So we're able to give not only scholarship to YMF, but also ASCE, which is really awesome. And so these are focused for sophomore, junior, seniors at either University of Texas Austin and Texas State. And so our main requirement is to be an active member of the student branch ASCE. The Austin branch is pleased to award 3 scholarships with a sum of $5,000 to deserving college students and members. Our first recipient is James Savage. James is a graduating senior with a 4.0 GPA from the University of Texas Austin with a degree in civil engineering and a minor in business. He has been involved with ASCE since January of 2021 and was involved in many other organizations around campus. For the last 2 years, he has interned and has gotten experience in roadway design, construction, inspection. James looks forward to making a career in civil engineering and sees it as an opportunity for future generations of more success and sustainable growth to ensure society will for many years to come. We are pleased to award James with $2,500 scholarship. Next, we have Victoria Weber. She is a junior civil engineering major with a minor in sustainable energy at the University of Texas Austin. She has been an ASCE member since her freshman year and currently serves as the UT Austin ASCE Sports Chair. Along with serving as a sports chair, she is a member of the UT Women's Club soccer team. Victoria she plans to enter into a growing sector of renewable energy. She hopes to gain and join a carbon capture company, a new technology that requires sequestering atmospheric carbon dioxide and storing it underground. We are pleased to award Victoria with $1,500 scholarship. Next, we have Kevin Yu, who is a sophomore pursuing a degree in civil engineering at the University of Texas Austin with a business minor with an elements of computing certificate. Kevin has been a member of UT Austin since his freshman year, where he served as the freshman representative. During this time, he effectively implemented in-person and online improvement strategies to increase freshman participation by 30%. Kevin's passion lies in the transportation track of civil engineering because he sees it as an integral part of society, offering the best chance to make a meaningful difference in people's lives. Beyond his studies, Kevin enjoys fishing, reading, and sports such as basketball and pickleball. He's excited to contribute to the civil engineering field. We're happy to award Kevin with a scholarship of $1,000. We actually have Kevin here to give a few words.
Hi everyone, my name is Kevin Yu, and first and foremost, I wanted to thank the ASCE branch here in Austin for their support. I feel like it's a priceless opportunity for me, not just financially, but being able to be here and meet all of y'all. This is my first time here, so I'm a bit nervous, but I would just like to thank all of y'all for y'all's support, and this scholarship will be able to let me focus on my class, focus on my extracurriculars without much worry this next upcoming semester. Thank you.
David's pickleball.
Thank you. Sorry, I don't have a graphic behind me. It's been sent out in previous newsletters, but I just wanted to let everyone know that this week on Friday at noon at Bolton Acres on South Lamar, we are hosting our first annual pickleball tournament fundraiser. As Tyler mentioned earlier, this is a great opportunity to invest in the future of civil engineering through our students and giving them financial scholarships to benefit their education. If you have any questions, you can email me at pickleball@austinasc.org. And we still have some sponsorship opportunities available. That is the only way to be able to enter the tournament as a team. All of our individual team entries have been filled at this time, but we still have openings for spectators. Anyone who wants to come and watch. We have our registration open on Thrive. You can go to Thrive, register as a spectator or as a sponsor, and be involved in this great fundraiser. So, thank you.
Hello, I'm Steve Zobel. I'm currently the committee chair for the Continuing Education and Professional Development Committee. And we're going to be having our mark this date, September 27th, fall continuing education conference. We got two people, one of them is in this room, they're going to be giving presentations. And it's going to be on the theme of best if used by. Think about that for a second. We all have a born on date, but we don't know when we're going to be taken away. So make use of what you have at the time you have. Use your profession, take it seriously, and train others to replace you when you're gone. And we're going to be, instead of meeting at the Pickle Research Center this year, it's going to be over, I believe, at the PDC, the Permitting and Development Center by the City of Austin. If you have any questions, please feel free to email me. I'm at steve.zobel, Z-O-B-A-L, @nwmdg.com. Thanks.
Everyone, I am doing the last student announcement. We do have our ASCE Texas section polls coming up in June. We have a very competitive president race for the Texas section this year. So if you are an ASCE member, I just want to remind you to go ahead and vote at the Texas section level. They provide a lot of support for us at anything government affairs, putting together a student symposium, and seat. Not to mention a bunch of other things they do for us. So just sort of really iterate the importance of the Texas section and remind everybody to vote.
Thank you, Kat. Next up, we've got our meeting sponsor today, SCI. If you'd like to come up and say a few words.
Afternoon, everybody. I just want to say thank you guys for having us as a sponsor. We're very excited and look forward for a very educational session here. So my name is Tanya Sonsing. I am the Texas Regional Manager for SCI Engineering in Texas. A little bit more about SCI. Founded in 1978 in St. Louis, Missouri, as Soil Consultants Incorporated. We provide geotechnical, environmental, natural resources, cultural resources, and construction materials testing. That's a lot of stuff. We'll go in there a little bit. We are employee-owned, small business, and we want to be part of your project team. We want to be more than just a checkbox to mark. We want to be part of the solution. So a little bit more about all those services. So your geotechnical, soil borings, pavement foundation design, retaining wall analysis, lateral pile analysis. We handle all that. We also, as a little sub niche, geophysical, ERTs, GPR, detecting your subsurface stratigraphy and USTs and other underground SU elements. Environmental services, phase 1, phase 2, ESAs, lead mold asbestos surveys, mitigation and monitoring, also noise analysis, SBCCs. Your natural resources, so wetlands, delineations, mitigation, 401, 404 permitting. So City of Austin, ERIs, TNE, your SWIP monitoring, we can provide all of those resources for your team. Your cultural resources, so your phase 1 archaeology, and cultural resource surveys, your categorical exemptions, architectural surveys. Had a couple more, but that's okay. And then construction materials testing. So that's your certified ACI technicians, ICC technicians to perform soils, concrete testing, structural steel, all of your other inspections for your special inspection permits. We cover all sectors, all markets, from your standard private commercial to transportation, education. We're just kind of a one-stop shop for all of your pre-designed. If you guys have on-site feasibility elements that need to be checked, we can help you guys with that. So I had our tech stock research on here. So all pretty much the majority of your 2s, all your 12s and 14s for the geotech. So we can help if you guys need teaming members or need any other kind of have subsurface or soil condition questions. So thank you very much for having us. I appreciate the time and I'll turn it over.
Thank you so much. Now our main event. Niko, would you like to join us on the stage? Thank you.
Appreciate it. Good afternoon, everybody. My name is Niko Kalos. I'm a senior structural engineer for LJA Engineering. And I'm here today to talk to you guys about the Three-Girder steel straddle caps that we did for the Loop 1604 I-10 interchange project in San Antonio. Before we get rolling, I just want to kind of gauge the audience here in the room. I know we have a lot of people online, but how many of y'all are structural engineers? Okay, we got a good amount of them. How many of y'all are in the transportation industry? Okay, so some pretty good amount of y'all will know a lot of the terms that I'm talking about, but I'll try to explain to some of those that don't, and we'll just dive right in. So what's a straddle vent? Straddle vents are what we use to support a bridge, usually over a lower roadway, all right? Typically that's going to happen over an entrance ramp or an exit ramp, frontage road. could even be main lanes in some cases, could be railroads. So it's on the screen, there's a few examples of what they look like. Those are all in the Houston area. And there are three common types. They're cast in place concrete with mild reinforcement or just regular rebar. And those are good for short spans. They're fairly inexpensive, and most contractors don't have an issue constructing them. Kind of stepping up the food chain, you have cast in place cap that's either, that's post tension, so you can get that longer span, handle more load. A little more expensive, takes a little longer to construct as well. You have to close traffic underneath when you do the stressing. Then there's also, precast caps that can either be pre-stressed or post-tensioned or both. And those are good for short spans. I think the technology is kind of, moving towards medium spans. And they're great because, you can get them in there quickly. But the reason they can't go that far is the weight starts to get prohibitive. So you can't lift them in place after a certain span length. And then we have steel caps. Which they're great for medium to long spans. They're great for low vertical clearance applications. And that's what we're going to be talking about today. So steel straddle bent caps. Historically in Texas, there are really three types. There is the box girder type, which is the picture on the top. And what that is it's a built up section. It's just a box, two flanges, two webs that are welded together. We call that the stacked cap. So the girders from the superstructure sit on the top of that cap. The second one would be box girder, again, same type of section, but it has the corbels or brackets on the side for the superstructure beams. And we use that for, low vertical clearance, right? So we can kind of eat up some of that superstructure depth. And the final type would be a box girder, again, that's integral with the superstructure. And that's that bottom picture. So those girders actually frame into that cap. And again, that would be used for when you have a continuous type superstructure and you need the vertical clearance. So what are some of the advantages of those box steel caps? Well, they can get out longer, like I told you, versus concrete. There's minimum closure to the roadway below during construction. So if that, frontage road or ramp needs to stay open, you can close it down in one night. You can lift the cap, set it, tighten it down, and you're done. And you can keep moving. They're easy to transport and erect because they're significantly lighter than a concrete cap. There's a reduced load on the substructure and foundations for that reason as well. So some of the disadvantages have been they're typically higher cost to fabricate and construct as a result of that. So the construction cost is higher. The box caps require the fabricators to work in a very confined space. So they have to, do those welds on the inside of the box. And that has a lot of issues like health and safety issues and stuff like that. So that drives the cost up. And the big one is historically they've been classified as something called fracture critical. And basically, I'm going to talk to you about what that definition is in a second, but just know that means that structure is extremely critical. If there is a fracture, the bridge will collapse. There's no redundancy whatsoever. So because of that, they require inspection every 2 years, which is tough for the districts, TxDOT districts to deal with. And they also have much higher material and fabrication requirements, which again drives the cost up. So let's talk about that redundancy. So fracture critical has been replaced with the term non-redundant steel tension member because professors like to make stuff up, I think. But anyway, I think it does describe it a little bit better. There's no redundancy at all. And you all can see the fancy definition up there from the FHWA. But the key is there's no redundancy. So if the tension flange has a fracture, the bridge will collapse. And so as the FHWA has, kind of defined this, they have given us, 3 ways that we can achieve redundancy. So the first way, which is the easiest way, is if you have 3 or more primary load members. And so the steel superstructure span you see in that picture has 4 beams, therefore it's load path redundant. No special requirements needed, right? The second one would be a system redundancy. essentially what that means is that you, as the engineer, have to prove that your structure can handle a fracture and not collapse. And that is, I think, something much easier said than done. The analysis would be pretty tough to do that. There are some simplified procedures that TxDOT's working on for like a twin tub girder system, like in that second picture. The third type would be internal redundancy. I don't want to talk too much about this. It doesn't really apply to what we're going to talk about today, but it's something typically that we'd see with built-up members that have gusset plates and bolts, and you know, that's going to be something like on a truss bridge that you would see something like that. So let's talk about the project. So the Loop 1604 I-10 interchange project is a part of the 1604 North Expansion project. Obviously, the owner's TxDOT. It's 23 miles long. That's the whole corridor. It's cut up into 6 different segments. LJA is the prime consultant on all 6 segments. It was the complete reconstruction of the existing interchange is in segment 2. And segment 2 had a 12-month design schedule. So it was very aggressive. And keep in mind, that's from the time the ink dried on the work authorization to when we had to have our plans ready to let. So keep that in mind as I talk to you guys more about this project. It was very, very fast paced. There's the project team. So TxDOT's the owner, LJ is the prime, the contractor is Williams Brothers, and their fabricator was WW AFCO Steel. So a particular concern to TxDOT on this project was to minimize traffic impacts. Some of you have driven through there. You'll see that the traffic is pretty tough, but it's because there's a very high traffic volume there. Obviously, I-10 is a major freeway, not just in the state of Texas, but the whole nation, goes from coast to coast. It's very vital for our economy. And, you know, 1604 itself is quite busy. Plus, we have some major institutions that come right up to the frontage roads of the interchange, UTSA and Six Flags Fiesta Texas. And as you might imagine, right around now, UTSA is generating some pretty big traffic movements, right? Graduation, got a lot of people leaving at once. And so because of that, TxDOT really wanted us to focus on trying to minimize the impact of all types of construction, specifically though with the bridge over the frontage roads, okay? So they wanted us to limit that stuff. So after we had laid out the bridges, we did an accelerated bridge construction study, ABC study, and we went through all the different components of the bridges and all the things that we had. But it wasn't just limited to the straddle bends is what I'm saying. But this is kind of a preliminary exhibit that we developed for TxDOT as a discussion point. And that's kind of a schematic of the interchange as well. You can kind of see the old clover leaf is going away. We're doing a new 8-directional DC interchange. And so what we did is we went through every single straddle bend that went over a road and tried to figure out what made sense there in terms of accelerating. Some of them didn't make sense. There may be some that are over a frontage road that may be closed for something else, so you could get it built without having to do anything fancy. But we went through there and we evaluated a lot of things, precast caps, and of course steel caps. And you see there, we had originally identified 7 of these caps, and at the end of the day, we ended up designing 9. So, you know, we knew obviously that the steel caps would give us a very good construction time versus something that was post tension. And also we had some spans that were very long. So there's, you know, without getting really advanced, we didn't find a good way for us to design those to be lifted, to cut them up so you can lift them. So we knew we were going to use steel. We had heard about a 3-girder straddle cap that had been used and designed on the I-91 interchange in Connecticut. So we reached out to the designer and the fabricator of that particular cap, Ronnie Medlock and Mike Colmo. Shout out to those guys. And we picked their brains and kind of figured out, you know, what went well and what we needed to do differently on our project. And TxDOT was very interested because, as I'll show you in a minute, there's 3 girders, right? So that means 3 primary load members, and therefore it is redundant, right? So we don't have to have those inspection requirements for the higher fabrication requirements. So we had some differences from that I-91 cap. The I-91 cap had a continuous trap box girder, and that meant that there's only one center line of bearing. So that was right at the center line of the cap, which meant they had no eccentricities on the cap. But we had simple pre-stressed beams, so we had eccentricity to deal with. Also, we had our caps kind of overhang the column on one side. They had what I would call a pure straddle, so it was just the columns and the straddle in between, all positive moment, right, all bending in that direction. But we had negative moment in ours to deal with. Also, ours were just much longer. We had 113-foot max overall was our biggest, 85-foot center to center on the columns. And then we had to deal with the challenge of, on certain caps, we had some TX70 girders, so they're 70 inches deep. And then on the other span, we had TX54s, which were 54 inches deep. So we had to deal with a big difference in the height of the superstructure. So I'm going to kind of walk you through the components of those caps. So got our columns here, and you notice the orientation of the column is kind of a little bit different than you might see a normal straddle. It's 90 degrees. And one of the characteristics of these caps is that they get very wide. So you have to, rotate the columns that direction. I'll tell you now that the steel we used was A709 grade 50 weathering. So because of that, we have drip pan. Then we have elastomeric bearings, nothing different than what you'd see on a steel superstructure in Texas. Then on top of those, we have our sole plates. Then we got our 3 girders sitting on top of those. So there's 3 eye girders. These are built up girders. For those of y'all that don't, they're not that familiar with structural stuff. You don't find these in the steel manual, right? They're not rolled. They're going to be built up. So you have 3 plates, they get welded together. But they're very easy to fabricate. The fabricators really like these versus the boxes. They're a lot easier for them to deal with. So on top of the cap, we have all of our components that support the superstructure. We've got what we call a masonry plate. Don't get too hung up on that. It's steel, but it's just kind of a term that's used in the industry for a bearing plate. And that supports our girders. It's very much like a conventional concrete cap on a concrete bearing seat on a concrete cap. And then where we had that big vertical difference, we had pedestals. And to kind of contain those and spread the load out, we had these bearing plates that kind of grouped along the length of the cap. And then to keep the water out, we have some sealer plates. Then we have our stiffeners, right? And if you guys have ever designed a steel structure, these are pretty typical, or nothing's fancy about them really. We have bearing stiffeners at the bearings, a jacking stiffener so that they can jack the cap up and replace the bearings in the future. And then we have intermediate stiffeners. And what we tried to do there is, we put our intermediate stiffeners underneath all the point loads coming in from the superstructure to support the flange. But they're also there to give us a place to attach the diaphragms, which the diaphragms are bolted to those stiffeners. And that's where the magic happens. And we'll talk about that when we get there. But those things is what makes the cap bend as one, and also has gives it its torsional resistance. And while, these things don't have to be inspected as frequently, they still need to be inspected. So we have the holes in their size for an inspector to step through. And then on the end, we have an access door. We have just a blank plate on the other side. And we've got FRP grading is what we use for the floor for the inspectors to walk on. And then on top, we just have regular conventional elastomeric bearings for the superstructure. So let's talk a little bit about detailing. Those masonry plates, the cap I was just showing you all was flat. It was drawn flat. Well, where we had these caps were at the gores. So they're not flat. They're actually angled, kind of like a housetop. There was a cross slope break in them. And so in order for you to deal with the variability of maybe the depth coming from the superstructure and that variable slope, we had basically a beveled plate. So those masonry plates were beveled. We capped their thickness at max of 4 inches. When we had a plate that needed to be thicker than that, we actually made a sandwich, and we had the bottom one beveled, top one was uniform thickness. And we kind of set them by taking a normal textile bearing seat and kind of setting it so that the long dimension of however that thing was rotated, we kind of set the length of the plate that way. And then they were just 2 feet transverse to the bend. Bearing plates, you know, I get this question a lot. We did not consider these plates as providing any structural resistance. So they were just there to spread the load out from the superstructure. They're 1 inch thick. There's no bevel on them. They follow the cap. And they were, you know, uniform width across the cap. And we tried to group them as much as we could per cap so that we can make fabrication simpler. And they were just bolted to the top flange. So the eye girders, for each cap, we had identical flanges and widths. So same dimensions, thickness, height, width, those are all the same for each cap. Remember, I said we had 9 of them. They varied from cap to cap, but on each cap, they were uniform. That was just to keep things simpler. You guys can imagine if you had to have a shop splice in the top flange, that could make it tricky with those plates on top. Like I said, we had to provide inspection access, so some of the dimensions were governed by that inspection. And this follows the TxDOT guidance that you'd have for like a trap box girder. We also set minimum thicknesses for the flange at 1.5 inch, and the web thickness was at a 1/2 inch min. We felt that just gave us a good starting point, and helped us, you know, satisfy a lot of the proportion requirements in AASHTO. Diaphragms, like I said, they're there to transfer the load between the girders, so they bend together. And they also are there to torsionally stiffen the cap. You know, the box caps are very torsionally stiff. You know, I'll tell you, the box caps are a lot easier to design than these caps are. So they're great for us, the designer, but they're horrible for everyone else that's involved. And these caps, these eye girder caps, are kind of the opposite. They're a lot more intensive on the design side, but once they're done, the owner and the contractor and fabricator have a much better time with them. And again, you know, on the outside, you can kind of see the doors that we had and how that opening kind of set so that it's kind of a continuous access for the inspectors. So the stiffeners, which the diaphragm's attached to, you know, that's the inspection hole size, 36 by 18. But the stiffener, where we had to reduce it for that inspection opening, it was too shallow, right? It wasn't big enough to support the flange. So we had to have kind of like a horrible style, you know, 45-degree bend in the plate there to get that full support. And we'll talk about the design of those stiffeners shortly. Sealer plates are nothing fancy here. It's just to keep the water out. That's it. You know, weathering steel is important to ventilate. And so that's another reason for the grating. It lets some airflow get into the bottom of the cap. Provides that walking surface, right, for the inspectors, and it keeps the critters out. You know, and that's really the reason we went with FRP, is that we could get a really, really small hole size. So we could try to keep out, you know, some of the bigger critters like bats and birds and stuff like that. The grating was attached to the flanges with stainless steel clips, so we didn't have to drill any holes into our precious flanges down there. Okay, so we're gonna get into the nuts and bolts of the design a little bit. In order for us to kind of understand how the forces flow in a structure like this, we're gonna have to kind of start from a simplistic fake beam, and we'll kind of walk to the real thing from there. So on the left side of the screen, the line beam model is just a fictitious beam. Let's say I have a beam and it's kind of set up just the way this cap would have had. So it has a little bit of an overhang. Y'all can see the little these guys right here are where the columns will be. For those of y'all that are not familiar with structural notation. So that's where the support is going to be located. And then everywhere you see an arrow, that would be like where we have a girder from the superstructure coming in, right? And remember, so we have a vertical load from that, plus we have a torsion. So that's what that little moment is there to represent. So if we took a very simple model like that, a single beam, you would see the following moment shear and torsion diagrams, right? I think, you know, pretty obvious. You're going to have a max positive moment. You're going to have a minimum negative moment, right? And, you know, correspondingly, you'll have a shear diagram, and then you can see that there's a torsion diagram there, right? Looks kind of like the shear diagram does a little bit, but Yeah, that's what that looks like. That's a very simple model. The grillage model, though, which is what we used, and we're gonna talk about why we used it, is where you basically split the three girders into three independent girders that are connected by the diaphragms. And that's what you see there in the lines that are going transverse to the cap. And so we apply the same loads at the middle girder only, right? And so what you see is something very interesting. So what happens is, if you look, M2 is the middle girder, and you're seeing 36% of this moment that we got from the single beam. And you might expect it should be about 33%, right? It's a third of the moment that we had from the simple model. But it's not, and it's a little higher on both the negative and positive. And we'll talk about why in a minute. But the main point there is that because those diaphragms are not infinitely stiff, they have a real stiffness. And so most of that load is going to go to the middle girder because that's where you have the loads coming in, right? But the other thing that's very interesting is on the shear diagram. And you'll see that on the middle girder V2, the shear is higher, again, because the load is there. But if you look, you'll see what's happening with the torsion. So there's no torsion actually in these members, almost none. Whereas our simplistic model said there was a lot, right? What's happening is that torsion is being resolved into a couple on the outside girders. So one girder is picking up a lot more shear force, and the other one is getting actually relieved on the shear force, right? And that's why you see the big differences between the shears on those outside girders. One has a lot more and one has a lot less. And that also affects the moment, right? Shear affects the moment. So you can see that M1 in this case actually is the design girder and not the middle one. That's the one that has the most moments. So just something interesting to see how that kind of works. So, the key thing is that those diaphragms, right? They have a finite stiffness. And so, if you look at the way this would deflect, if you put a force on the middle girder, the whole thing is going to bend a little bit. And as it bends, you will have three unique displacements, U1, U2, U3. And when we apply that torsion, we'll have kind of the same, except the middle girder will not really deform. It will rotate, but it will not displace vertically. So we chose, if we look at now kind of dissecting the grillage model. So let's take out those components of torsion and just look at the vertical load, which is the gravity load tab. You'll see there that we are much closer to 33% on all the girders, right? So we took that torsion out so you can see that they're bending about the same. But again, the shear on the middle girder in that case is higher. Again, because the diaphragm has a finite stiffness. And then you can see what happens with just the torsion on the right. And that's that effect I was just telling you about. There's no shear at the middle girder, and those outside girders pick up a couple, which translates into additional moment as well. So we had a lot of ways we could design these things. Here's a few options all the way up from the real simple A all the way to full plate model FEA analysis. Keep in mind, by the time we were done with that ABC study, we were probably already 4 months in to the project. So we went with the grillage model. It's well understood, and its limitations are understood as well. So that's what we went with for this particular analysis. So here's kind of a close-up look at the model that we used. We have the grillage model on the left is what it kind of looks like in STAD. We use STAD for this analysis. It shows the full-blown system with the cap and the columns and the foundation. We separated those. We only did the cap really in STAD and then took the loads out and designed the columns from that. But the way the model looked like is we had our plate girders with the exact dimensions of the plates in STAD. And for the diaphragms, we modeled them as a fake plate, okay, that had an equivalent stiffness of the real diaphragm. And we'll talk about how we calculate that. And then what we did, our loads are not applied at that middle girder, right? And they're not applied off the center line of the other girders either. So they're offset a little bit. So what we did is we put rigid elements to that are infinitely stiff to model that moment arm that you have from the center line of the cap. So the diaphragms, we thought long and hard about how we were going to capture the model that from both a stiffness perspective for the global model, but also, how are we gonna design it, right? So we had an idea that the behavior of these diaphragms would model something called a Verendale truss. What that means, from some of y'all might remember from statics, that trusses typically have no moment. They're either tension or compression, right? A Verendale truss is a moment frame that you make a truss out of. So it's a little bit different, but it looks like that. It's kind of like a box. There's repetitive boxes. So we looked at, okay, we did one full-blown finite element model, which you can see on the very far right, that mesh that was there. And we compared that to the, so that's U3 was our displacement that we got. We compared that to the displacement we got from Verendale models, which is U1, shown in that figure, and we got very good parity. So we're like, okay, we feel like it is behaving as we think. So we said, okay, we kind of have a simplistic version too. What we did is we kind of look here, we put a support right where that inflection point is, and kind of tried to reduce, even simplify it further to make it easier on ourselves. And so we saw U1, U3 were coming up very well. But like I told you in our model, our global model, we wanted to use just simple, fictitious plates. So we know the thickness of that plate, which will be the actual thickness of the diaphragm, but we need to find the depth so that we get an equivalent stiffness in our model. And so really what happens if you break down what's going on, there's basically a simple beam that has a load applied at the middle, and then you have two rotational, you have two springs that are rotational springs at the center lines of the exterior webs. And so when we kind of came up with that analytical expression for U2, we confirmed that meant U1 and also U3, so we felt good about what we had. Okay, so that's kind of what we did. I hope I didn't lose anybody there. There's a lot of equations there, but it's the Verendale truss is pretty well known, and we use that as our guidance here. So what did we check on the design? Obviously our eye girders we check just like any steel superstructure. So if y'all structural engineers out there familiar with those, it's very similar code checks. We checked the girders as non-compact sections. We had to add in, there is some lateral bending. So we put the typical third of that lateral bending stress in with the bending stress. We looked at a lot of local states, flange plate buckling. You can see there where the flange wants to buckle, a slender local bend buckling of the slender webs we looked at as well. And then lateral torsional buckling. We had to look at that, from a global standpoint. So the cap itself wants to buckle the whole system. And so we had to check that as well. And then for shear, we ignored tension field action and just designed as unstiffened sections. And made our lives a little easier. And of course, we checked, the cross-sectional proportion limits, welds, bolts, tons of stuff, right? And of course, fatigue was also a big check we had to make. The stiffeners, nothing too crazy really with the stiffeners. Again, be very similar to something you'd see on a steel design for a superstructure. We did have to look closely at how we were going to deal with that corbel, the 45-degree deal. We don't have time to do finite element analysis on every single one of these. Every CAD might have had, 12 diaphragms, and we had 9 of them. So there's just no way. We just didn't have time. Even if we had the budget, we didn't have the time. So we did a few finite element, models to validate our approach. You can see one of them there where we're looking at, how the stresses move. But what we did was basically break it down into sort of a free body diagram for how the forces move. We sized our welds like that. We sized the thickness of the stiffener. So again, we use a lot of FEA as a guide for our more conventional analysis, right? To make sure that we had a sanity check. Are things coming out the way that we expect with our simplified models? The diaphragms, we went on, we really dug into this. How are we going to design it? We got to approach the stiffness, which is how we get the hold cap, right? but how do we design the actual diaphragms? And again, the accurate way would be to do it with an FEA model, right? And you can see we actually ran one, like I said. But we, then maybe something a little bit less complex would be to use the results we get out of the Verendale frame, kind of the full blown one. But at the end of the day, we decided we stuck with kind of the simplified Verendale model, which is on the very left, quick check. We did see here that there was a little bit of more of a difference in accuracy between the FE model and our quick check. So what we did is we just way dropped the allowable stress that we were going to use for the diaphragms. Help us sleep at night and know that we have a little bit extra capacity. And guys, this was the second one in the United States, right? So we did that in a lot of places. We didn't go down to 1.00 on pretty much anything. We put some conservatism in there. Make sure I'm good on time. So the masonry and bearing plates, they're pretty simple. We designed them like little cantilevers, and that kind of bend by the center line of that stiffener. Remember, we have a stiffener under every single one of the bearings from the superstructure. One thing I forgot to mention is where we didn't have a diaphragm at every single stiffener. Sometimes we had two girders that were coming in very close to each other, and we had to have a stiffener that was maybe too close to a diaphragm where they have to have access for bolting and stuff like that. So there we only would do a stiffener. They would be standalone and did not have a diaphragm. So these plates, we set the point of fixity at the center line of the stiffener, and we basically proportioned the stress that they got from bending to each one, based on its particular stiffness. So some of these things were different. Like the flange was normally thicker than the bearing plate, for example, so it would get more stress. And so we went through and proportioned the stress that way. But they all acted, we didn't act like it was one big plate, in other words. They were all three separate plates. And then some miscellaneous items, we had those pedestals, they had to be checked where we had them, where we're basically looking at bending and shear in each direction. The top plate, you need to check for bending and shear. The diaphragm bolts had to be checked. So we had to go through there and check all those bolts. All those bolts had to be, those are main structural bolts. We had to do live load deflection checks, and we used typical ASCE L over 300 for the cantilever and 800 for the main span. I will tell you that deflection actually controlled the depth on several of the caps over strength. And then we also had to check the elastomeric bearings that were underneath the caps. One thing I didn't talk about there, how we modeled the bearings was we had one that was fixed and one that was expansion, and we put the expansion bearing underneath the support that was getting the most load so that we could satisfy our slip and rotation checks. But we had to look at a lot of different things because the interchange is being built in phases, and so there's several instances where, right at the gore where we have two DCs splitting off in plan view there, one of those DCs is going to be open to traffic before the other one is constructed. And so you may have your torsions are going to be higher there than you will have in ultimate service. So we had to look at those things very closely. We also had to look at construction items as well. A lot of people ask me about what we did there. We, on a case-by-case basis, we had to look at, do we allow or disallow a certain sequence, right? Like, ideally, we don't want one side to be completely constructed and not the other. So we wanted to kind of go with beams on both sides, then pour one of the slabs. We're in cases like this, we did have to consider that stuff. So here comes the fun stuff, the pictures. So you can see here's a couple of the caps in the fab yard, and they can give you a sense of size. You can see the man standing there working on the inside. This is when they're all nice, shiny, blast cleaned, you can see up there that the cap on the right has the pedestals, and the cap on the left has no pedestals. That one had uniform superstructure depths going front and back. There's just another shot kind of showing the inspection access before they put the door in there. It's a tough job going in those things. I'm glad I'm not doing it. Then there's a close-up of those bearing plates and the sealer plates. something interesting to note there, they actually opted to ship those, caps with those plates, separate. So they fit them up in the shop, made sure everything, was in alignment. And then they took the plates off and just put the cap on a truck, and then they put those, plates separately. I'm not really sure why they did that. But that's what they elected to do, and then they just bolted them up and they got them to the field. Here's another shot. That was the one we had displayed earlier today, and they're currently under construction. These are the first two that were put up, and you can see now they've weathered, and they have that nice patina. One of the things that we were a little concerned about early on is how they were going to look compared to a box cap, which looks very clean. And these things, when we were doing some 3D renderings of them, we were a little concerned. They were a little industrial, I guess is how you could say it. But I think they actually turned out really nice. And they do kind of blend in really well. There's a shot with the beams on those very caps. That was a few days later, they put the beams up. So I'm kind of at the end, and I just want to say first, I really want to extend my thanks to TxDOT for giving us the opportunity to design these and trusting us to design these. And they've always been a very pioneering organization, and so I just really want to thank them. And also, I'm just a guy up here talking about this. I was a part of a team, and I really want to thank all of them for their efforts. I'm by far not the smartest person that worked on those caps, and I think it was a true team effort. Like I said, we had 9 of them, and we got them all done. We got very good feedback from the fabricators. There was basically very few questions during the shop drawing review phase, and they built them. And they loved them. They the guys that are actually doing that stuff, it's just like, this is way, way easier. And, they didn't have to meet any of those fancy requirements. And, the cost was, I would say, was a little bit less than what I would expected, but this is a huge job that has millions of pounds of structural steel. And so I think a little bit has to do with that economy of scale. So if you just had maybe one of these on your project, expect them to be on the order of a box cap, at least until they kind of catch fire in the industry. So, and with that, I'll open it up for any easy questions, please. Easy. Yes.
You mentioned cost. What's like a order of magnitude cost comparison, something like this compared to like one of our.
Okay, the question is, how does this cap compare cost-wise to like a conventional cast in place? It's more expensive. I would say they're probably 30 to 45% more. And that's, don't quote me on that. I can actually get you a real number. I should have looked at that before I came here. I have we have the bid tabs, but again, I don't have a good picture because like I said, I think there was like 19 million pounds of steel in that job. So there is a lot of steel there. If you had just one, like if you're doing one DC or maybe a 2 DC project, it could be probably more than 50% is what I would expect. They still have a time and place. I gave this talk at the ASCE conference, and there you can't talk about concrete. They don't want you to say anything about concrete. So here though, I'll tell you, it's not going to replace a concrete mile cap. That's not what it's going to do. If you have a 50-foot straddle, more than likely you're going to use concrete there, but it's all dependent on how much impact you have. Road user costs, for example, we ran the numbers there, and that's what TxDOT was kind of seeing. Like, it's this huge amount of impact to our citizens, so it's worth spending the money up front. Yes, sir.
You have to take that load questions and bring it into account for the places themselves.
Yeah, we the camera was something we were really kind of concerned about, especially where you have 3 different ones. But we did, we had to look into what those deflections were, how we were going to camber them. The good thing we had no vertical clearance issues on these, so that was a good thing. So if they deflect a little bit more than we expect, it's probably okay. And like I said, on the serviceability check, we made sure that there's plenty of stiffness in there so that we're not right at that line. If it's 2 inches of deflection, we made sure that we're going to deflect 3/4 of an inch. So yes. They're just regular elastomeric bearings with the steel, the steel plates. We had, so they had anchor bolts on There's two anchor bolts on the exterior ones, yes. Yeah, they're anchor bolts on both sides. And then, like I said, one of them was expansion, so we had a slotted hole so that they can move, but one was just a standard hole, two anchor bolts per girder. That's the way it worked. Yes. Yeah, that's a great question. We got it on the other one. The question is, did we paint the inside white for inspection? Very common on tub girders. And the answer is we did not. We did not do that. You know, there wasn't any guidance there, really. I mean, the tub girders, they typically would do that. But again, in theory, these ones shouldn't have to be, up to that level of inspection that they have historically. So we did not paint. All right. Well, I really appreciate ASCE Austin for having me out here. It was a pleasure.
We go ahead, we've got a special little prize here, coming out, speaking to us. Can we get the attendance count for today? Awesome, thank you so much. Next month, we've got a special project spotlight for Waterloo Greenways to Confluence, so be sure to get your tickets for that. And we'll see you next time. Thank you all so much.
Thank you.